Let's start. Good morning, everyone. I'm Jacopo. Today we're gonna talk about intent-based network isolation in Kubernetes. Before diving into the topic, a little bit of presentations. Who are we? I am Jacopo Bufalino. I'm a doctoral candidate at Aalto University, and I'm also a researcher at CNAM, which is another university in France. Together with me today, there is Jose Luis. Please introduce yourself.
And welcome today. And yeah, we met doing the PhD here in Aalto, and currently I'm also doing a project with the Polytechnic University of Valencia and the Valencian Research Institute. So yeah, nice to see you here.
Okay, so what are we gonna talk about today? So today we will bring you to our PhD journey, which spans across the Kubernetes networking stack. We're gonna start with our main objective, that is understanding the limitation of Kubernetes networking, at least how it is used today. And to do that, we're gonna go through three main research questions. First, we want to show how and why the Kubernetes network stack is not fully in control of the orchestrator, meaning that Kubernetes doesn't know that much about the underlying networking. After that, we're gonna move to another problem. That is that it's very hard to translate higher level objectives into network policies. This means that, for instance, when you have a lot of third-party applications that we install in our clusters, it is kind of hard to understand how to merge them together and how to combine them in terms of functionalities, but more importantly, in terms of network policies, how to connect them.
Oh, sorry.
And third, we're gonna also look at how LLMs are playing an important role in network segmentation and what are those limitations. And to do that, we're gonna have three goals. The first main goal is that we want to challenge how networking is handled. And we wanna engage with the community to see if there is room for cooperation and so on. And to do that, we have three sub-goals. So first is we want to understand how the connectivity flows in a Kubernetes cluster. So how connections go from one place to another. Then we will also have a goal to generate baseline network policies for those unknown applications. We can think about them as Helm charts. And finally, we want to challenge and improve the way network policy generation is handled via LLMs or large language models. But since we are researchers, we always start with background. So in this case, it's not going to take long, like 25 minutes of background, but we start with very from the beginning, which is Kubernetes networking model. It's going to be like very, very fast. So what we have in Kubernetes is the essential compute unit, that is the pod. Each pod has assigned a virtual Ethernet interface and a loopback adapter. Pods are like creation and deletion of containers within the pods is handled by the so-called container runtime interface. That could be Docker or I don't know, Podman, whatever. And the communication between those pods and also between higher entities like services is done with by using another interface, which is called the CNI, the Container Network Interface, that is essentially responsible for allowing or denying connectivity. The problem in all of this is that, like we're gonna look at later, neither the CRI nor Kubernetes know exactly which port is open in a given container at a given time. That information is stored and buried within the operating system, and this information never surfaces. And we will see why this is a problem. But of course, why are we talking about Kubernetes networking? Well, the idea is that Kubernetes has become so powerful and so important that not only has attracted the broader open source community, but also hackers. In fact, as we can see, a lot of novel attacks have been developed specifically for Kubernetes. And that's where our research starts. We started looking at the attack surface of Kubernetes. To do that, we refer to the MITRE threat matrix, specifically designed for Kubernetes. And within that threat matrix, we started focusing on the networking side. So we looked at this column there, the lateral movement column, which basically tells us all the different actions that an attacker can perform in our cluster once they have a foothold in the system. And to do that, we simply collected those techniques. And if we zoom in, when we look at lateral movement, we see a lot of information regarding host path, core DNS poisoning, and IP spoofing. But in reality, the view that they give us about the possible attacks is very limited. In fact, if we group those threats together, we see that there are a lot of container-based problems, control plane-related problems, but for the networking problem, we only have few information. That is basically, if you have ill-configured policies, then things may go wrong. So that's where our research starts. And for this research, so we said that we have 3 goals, and we start with the first one. The first goal is to understand the internal network, internal cluster network state. So the idea is that we have this discrepancies between what is actually listening on a container and what the Kubernetes YAML files tell us. And we want to see how this maps to real applications and to real clusters. So to do that, we started looking around at open source projects if there was any tool that could help us, but there was none. So we built one, and we'll release it for the open source community, and it's called KubeSound. With this tool, it's like what it does is very simple, although the infrastructure definition and the diagram here may seem complicated, but it's essentially a distributed Nmap. So we go into each pod and we start analyzing the possible connections from each pod to every other pod. And we do that smartly in the sense that we know the ports that are open into each container because we can look at the OS level information for that specific namespace. And so it doesn't take that much time. But the idea is that now we have a tool, we have a way to map the connectivity state of the cluster. And here is an example of the things that we have found. So here is a simple application, although we don't, there should be some edges, imagine them. And basically, we have the database and an application, could be a WordPress application. And when we analyze it with KubeSound, we started seeing a lot of unwanted communications. For instance, we noticed that the database was able to connect to the internet, which database should connect to the internet in a normal scenario, not that many. Also, we noticed that the database was able to access the front-end application, which again, it's not something that we want to do in the first place, and so on and so forth. So in the end, a lot of connections that are possible in the cluster are not something that is interesting to us. We want to prevent that application, that connections to happen. But before KubeSound, there was no way of noticing that. So we now have a tool with this KubeSound. We have a tool to capture the connectivity state of the cluster to see for real what is possible, what can I reach from a given location in the cluster, and what can we do with that? How can we leverage this to find something interesting? So we have seen that the reality is different from what appears from the YAML configurations. And then we started saying, okay, which type of misconfigurations can happen? And how can we get policies when we don't find them? How can we generate policies based on that? So what we did, we went back to the scratchboard and we started looking at the differences that we were seeing from popular open source applications compared to what the real system was. So we looked at the YAML files and the and then the actual state of the cluster. And we created a list of things that can go wrong. So for instance, in many cases, we see that there are open ports in a container, but those are not described anywhere, which basically allow access to those ports. We also have the opposite case, where we have ports that are declared on a container, but those are not open. Then we saw other interesting patterns, like random ports, dynamic ports being allocated by services, and those were not tracked by any network policy. Then we also saw another issue that we called label collision, where you have multiple services that have the same sort of labels, and those interact with each other, and sometimes they can break up the application flow. And of course, the usual suspects, lack of network policies and container binding to the host network. So what we did, we collected this set of issues, and we started looking at open source projects if they had those type of issues. And what happened? In 1 month, we fixed over 40 misconfigurations across open source projects, which tells us that the network misconfigurations are a real threat happening in the wild. And there is usually this misconception that people actually believe that what they find in the YAML files is actually the content, what is actually running in the system, which is completely wrong. So now we are left with another question. So the question is, now that we have a lot of components, that we know that the system is not telling us the truth, how can we create baseline security policies that actually help us preventing many of these instances of misconfigurations? And for that, we need to go back to the drawing board and start figuring out a solution that could automatically generate policies, especially for third-party applications, because of course, who cares about our applications? We know them, we know which ports are exposed, but when we start importing more and more applications like Helm charts, then we are responsible for infrastructure that is written by third-party people. And in principle, we shouldn't be knowledgeable about the internals of the applications, but due to this problem, we are. So back to the drawing board, and let's now create network policies for these unknown charts. And for that, I'm going to leave the floor to Jose, who's going to tell you more about this other part, or the second part of our research.
Okay. Do you hear me? So yeah, for this second part, thank you, Jacopo. We developed a tool that we call Helmet. And basically, what we did when we are thinking about how this tool should approach this problem is, first we took a look at how isolation is looking in the state of the art. What are people actually already doing? So of course we have namespace-based segmentation, like a best practice where you want to isolate the things logically in your cluster. But of course, that's maybe not as fine-grained as we would like. Then we have tools like, for example, source course-based policy generation, that they take a look at the code and then try to create those network policies based on the code of the applications. And then also traffic-based policy generation, with a new vector being one of the available commercial solutions, that basically they sniff the traffic, or maybe you have like the traffic already logged, and then they generate network policies based on that information. So this was the state of the art when we started working on this problem. And what are the challenges of solving this issue? Like, okay, we already have those solutions, why they are not enough? Well, as Jacopo was mentioning, when we are importing a chart, maybe that chart actually has dependencies. The third party has a third party application. And by default, if you don't have enough network policies, that means even the dependencies of the application you are importing can access everything network in your cluster or namespace if you already have some policies there. Then another challenge is the source code may only have like a narrow vision. It's actually quite hard to understand all of the endpoints or all of the possible combinations in terms of connectivity that an application needs just by looking at the source code. Or maybe the source code is not available at all, because you have just an application that you are downloading, but you don't have like that as an application that you have developed yourself. And then when we look at what are the problems with the traffic-inspired approach, is basically when are you done with the traffic analysis? Do you have testing enough that you can capture all of the endpoints that your applications are going to use in the whole life cycle? Most of the time you don't. So based on this challenge, then our goal, of course, is to reduce opportunities for lateral movement. If we imagine that one of these applications that you are going to install in the Helm chart is vulnerable already, has a vulnerability, can we reduce what that application can access within your cluster? And then what we do is we first want to automatically generate the network policies for this application. As Jacopo was mentioning, for applications that you don't know all of the internals, you don't need to know all of the internals to just deploy in your cluster. We want to do that before deploying that into production. Of course, for the traffic-based, that's one of the problems of the traffic-based approach, is that you need to run the thing to learn the network policies. We want to go one step before that. We are assuming we don't have access to the source code. And of course, we don't want to break the application. This is another issue, that if you don't limit enough, of course, the adversary can have more access to your cluster. But if you don't allow all of the connections in your network policy, then the application will fail, and probably on a Friday afternoon. So with all of this, we create the helmet, and basically what we do is we use the natural boundaries of the application to build the network policies. This is inspired by more than 40 years old research on software engineering, which is basically modularity. That means that the software can be naturally grouped into modules. Information hiding, that means when you have a software that has many items, not everything needs access to the rest of the code. And the hierarchy, because again, you usually have a main application and its dependencies. So we take all of this, all the theory on software engineering, and we apply to Helm charts. And then the solution we built basically is based on creating two connectivity graphs. This is an example application of Prometheus, and we have Prometheus and 3 dependencies that he's importing. We can check the dependencies on the Helm chart definition that you can see there. And first, we are going to build a connectivity graph based on this configuration. This basically means that, of course, the main application Prometheus can access everything that it contains, pods and whatever. And we apply the hierarchy. The main application can access the dependencies, but by default, the dependencies cannot access each other or the rest of the cluster. So think about a main application that is importing libraries. We're applying the same thing that usually you can find in other types of software to Helm charts application. But of course, this is maybe not enough, because of course people like to create software in different ways. So to complete this part of the connectivity graph, then we look at the configuration. We specifically are trying to see if there are environment variables that give us hints of other types of connectivity that doesn't follow the hierarchical view. So in the case of this example, we find an environment variable that points that the Grafana do actually need access, or is going to try to access Prometheus, because otherwise you will not put that environment variable there. And combining these two graphs, we end up with the whole connectivity graph of how the connections in this Helm chart are going to look like. So we take this, and then what we did is we downloaded all of the Helm charts that were in Artifact Hub. Around 450 can actually be run because of course people upload a lot of crap there. And from those 450, then we apply our methodology, and we found out that around 85% of those Helm charts can actually be automatically secure. This means we can take the application, we can generate those network policies, apply them, and nothing breaks. For those that break, we also develop a high-level policy language, so you don't need to start looking at the ports or the everything, but you can just say, okay, I want this part of the application to be able to connect to this or not. In most of the cases, applications are breaking because of what we call sibling connections, dependencies that actually need to talk with each other. So if you have this application where the main application is the proxy, and then the web server and the database are the dependencies, then you want to allow, for example, the web server to access the database. This is an initial connection that by the hierarchical view we will not allow. But in this case, we can just edit the file and say this part can connect with this part, and that's enough. This was the second goal, the second piece of our research journey. But then from here, we start thinking, what else can we do? We can already add this baseline. And the next goal will be how to convert user intent into policies. Let me explain you a bit, because this is a bit technical. So what do I mean with intent? Intent-based networking has existed for a while, and with intents, what we want is to translate high-level objectives from the user into provision infrastructure. So in this case, before, what we have is just security baseline approach. This can be an intent. So given this application, please generate a security baseline for the application. Here we're moving into more broad goals for the user. So the user may want to, for example, take an existing network configuration and translate it to another CNI or another type of architecture. Or you want to, what we mentioned about the user defining the connectivity, you have a cluster with many applications, you want to add one, and the user can define, okay, I want this part of the Helm chart to connect to the database, to be able to be accessed by the logs or any other things that are running on the cluster. So this is what we mean with intent-based networking. But of course, our focus is still on secure configurations. You will find other use cases where they use intent-based networking for also provisioning service or applications. In our case, we are still talking about network policies and secure network policies. So where are we now on solving this issue? Well, this is a talk from KubeCon last year, done by Red Hat and IBM research people, where basically they are comparing, similar to what I have described, their static solution, and then the next step, using LLMs for this intent-based networking. And the conclusions, at least this year, was that the LLMs are not ready for the job. So of course, we like challenges in academia. So okay, let's keep working on this. And it's not only because it's difficult or we think we can do better, but basically, instead of expecting, their approach is basically, I ask the LLM to generate the network policies and is either correct or not. So we think that can be improved, and we can build a pipeline that better solves the problem, not only with the LLM, but using many other stuff. But of course, that was last year. If we think about what is happening right now, people are using agents. So basically, you deploy an agent in your cluster, the agent has access to the cluster, the logs, the network traces, and based on that, the user interacts with the agents, and then the agents gets the job done. That is the idea, and this is happening. Of course, the more access you give the agent and the more data, technically it will work better, so it's encouraging to give more access to this platform. But this also comes with its own set of problems. Of course, as any LLM-based solution, you have hallucinations. You can have like incorrect labels on key values on the output of the network policies. That will be a basic problem of correctness. It's also difficult for the LLM to capture the peculiarities of the network policies, of the network model. Not only you have already existing network policies, but you have the defaults, and kind of incorporating that logic into the LLM is not easy. And by default, of course, they are only generating text. They may not have that model within them. There is also a problem of granularity. This, of course, when we approach this problem, we already learned a lot of lessons from our previous research, and we know that you don't want too permissive policies, but also you don't want to be too strict and break the application. And of course, asking the LLM to do that is quite difficult. And then the lack of verification when we're thinking about a pipeline that uses LLM, of course, you want to check and verify what are the results and have a more programmatically way of understand if the solution that LLM offered is enough or not. And lastly, because we come from security background, of course, the idea of having an LLM or an agent to have this broad access to the cluster is make us uneasy. So we would like to avoid that. And this, of course, has already created security issues. And you may have seen in the news this AI agent that after deleting the whole database was like, oh, sorry, I violated every instruction you gave to me and decided to destroy the business. So trying to avoid this, what is our solution? Well, this is a bit small, but you can check the slides later. Basically, we start with the user that, we start with the user that expresses the intent. And in parallel, we are going to use Kubeson to capture the real, like a screenshot of what is the connectivity within the cluster. So paired with that and the intent, we are going to use an LLM and try to reason first about what the final state is going to look like. So if these are the connections right now, and this is what the user wants, how the end state of the connectivity is going to look like. Then this ideally will be reviewed by a person, and okay, this is exactly what I wanted. Otherwise, you can iterate a bit there. Or you could, if you are brave enough, you can have the pure agent solution. But the idea is that if everything is okay, that will be deployed in the policies generated by the LLM will be deployed in the cluster. Then we run Kubeson again, and we're going to capture again what is the state. And then we're just going to compare, we have the validation. Is the final state, is the current state on the cluster after applying the network policy, the final state that we thought is what the user wants with his intent? And then if it's okay, then yeah, we are good. Otherwise, we are in a loop. We can go to the LLM again and say, hey, based on this intent and the state that the cluster was, the network policies didn't end up on this state. We have this situation, and then you can iterate over it. So this is, again, our solution, and thinking about not how to solve the whole problem with just you put the AI, you spend all of the tokens, and then you solve the problem, but how can we use LLMs in a smarter way? So this is where we at. We developed this solution. We are now doing the evaluation, and at least with the synthetic intents that we have, the results have been really good. From the security, this is a security and privacy-oriented solution. This means that our LLM doesn't have direct access to the cluster if you don't want, and actually it can be run just independently, completely of the cluster. It only needs the intent and the output of Kubeson. This can also be like a good option if you are worried in terms of privacy, because when you could change the labels, you could change the application, the LLM doesn't need to learn what you have on the cluster. It doesn't need labels to assign them. With this, we're showing that LLM only is not the solution, but you can inform the process and pipeline it in a better way. And again, that we need verifiable outcomes. You need to know if what the solution that you are applying is correct and is enough, and then otherwise iterate over it. So this will be the end of the presentation. After all of these 3 projects that are part of our work, what are the takeaways? We have seen that there is a gap between the Kubernetes network configuration and the actual connectivity, and that's a reality. Ideally, not everybody that works on Kubernetes needs to be aware of this, but as things are today, this exists, and it's a problem. Then supply chain issues go beyond the application code. And so right now, when you think about supply chain, is most of the time you're thinking about the source code of the applications and finding vulnerabilities there. But what we have seen is that importing third-party applications and having third-party infrastructure is part of the supply chain, and you need to be worried if that's part of how your company works. Then we also have we have shown with our research that intent-based networking is achievable with LLM support, and that it can be done without this full access and full source of data and giving all the power to the LLM, but in a smarter and more secure way. And finally, long-term, I guess, and this is something we both think, the network configuration should be enforced by Kubernetes and not like give the current status as it is right now, because this will remove all of these known issues that what is configured in the networking, the pod information, the ports information, that is kind of wasted and doesn't reflect what actually is happening underneath. So long term, we will not need all of this, and Kubernetes could handle this in a smarter way. But yeah, thank you. This was all of our presentation, and if you have any questions, yes.